Good morning, ladies and gentlemen. I will present you the results of my own research concerning the topic historic and modern buildings in the life cycle. This is a main concern of my team, and I will bring you the basics concerning the theory behind what does it mean to consider the life cycle for buildings, and secondly, what does it mean to consider the life cycle in an economic and environmental aspect. And so I present you the life cycle concept, which we have developed in our department. Basically, I start from the beginning. That was at the times of the Rio Conference 1992. There was new terms created, which are called the 3 pillars of sustainability for buildings. And the 3 pillars are environmental sustainability, economic sustainability, and social cultural sustainability, which does mean that environmental, which we consider in this presentation, optimize resources, cycle of materials. What I will present you is how to measure, how to calculate this type of environmental sustainability, considering the whole life cycle, or at least the whole utilization cycle of a building. The economic sustainability considers a long-term optimized cost-benefit ratio. That does mean how can I calculate at the beginning of a refurbishment or of a new building, how much costs this building considering the whole life cycle. And last but not least, the social cultural sustainability, which will not be treated in detail in this presentation, but this is also very important, especially for monument protection and cultural heritage. This is a main aspect of our social cultural sustainability of buildings. What is a life cycle? The life cycle, and this is here an overview, is the consideration of a building beginning at its planning stage. That means it's just an idea, and the planning will be started. Then the construction of the building, then the new building is completed. Then the long phase of operation and use, intermittent with refurbishment phases, and at last the demolition and disposal of the building. This is the life cycle. And let us consider the economic life cycle. Due to the past, I was always wondering, or people were always wondering, if they are built new buildings, they detected that the follow-up costs of new buildings are much higher than the follow-up costs of the building of the last generation. And this trend started in the 60s of the last century, and more or less up to now, we have the problem that our buildings are too high in follow-up costs, not because of the energy consumption, which is only a minor part of the follow-up costs, but of the building technology. Building technology is a so-called cost driver. We detected, and so we analyzed a lot of buildings concerning the economic life cycle. The basic, we are very proud in Austria that it was possible to make an own standard, especially for the method of life cycle cost calculation. This standard is Austrian Standard B 1801-4. And the result is total life cycle costs in euro, or you can also consider what is for benchmarking important parameters like euro per area or euro per year, excuse me, or euro per square meter prime area, what the technical term of used area in the building. And these parameters, these life cycle costs, are the parameter to measure life cycle oriented economic sustainability. And it's also to add that it is not the total sum, the interesting point. The interesting point is the matrix of all numbers we can calculate. That means we have so-called cost groups. Here you see in this picture, you see the main cost groups due to Austrian Standard B 1801-2, in which the construction costs and the follow-up costs are standardized. You have, let us start with the construction costs. You have, that is the first row, 0 is ground costs, then number 1, ground development, number 2, construction structure costs, number 3, construction engineering costs, number 4, construction finishing costs, 5 is interior, 6 is outside facilities, 7, planning work. All planning work is also part of the construction costs, supplementary work, and reserves. And the follow-up costs are administration, technical operation of building, supply and disposal, cleaning and cultivation, very important. This is, nobody knows, or just a few people know that cleaning and cultivation is a main cost part in the follow-up costs of a building. Security services, facility services, overhaul, renovation and refurbishment. That's in the main thing, that the big maintenance things that we have to do, and other costs, and at last, removal and demolition. This is per definition the first level cost structure. It is also important to mention that normally in calculations we consider the costs without value-added tax. So you have to take care of the value-added tax, and you can do the calculation in both ways, excluding value-added tax or including value-added tax for all costs, so that you compare the costs. And on the right-hand side, I show you here, on the right-hand side, this is mainly the definition of the life cycle costs. And you see this considers all costs, the main groups from 1 to 9, and then the rest. What is also important to say is that there are no financing costs within the life cycle cost calculation, because of the fact that we consider the costs in the form of discounted cash flow. And discounted cash flow means that all costs will be considered at a certain point of time, and this type of consideration cannot, per definition, include financial costs. Then we go to the next part. This is environmental life cycle. The environmental life cycle is much more complicated than the costs, because you have to consider the whole phase of the material flow over the life cycle of a building. And this starts much earlier than life cycle costs, namely before the planning phase. There is a phase, production of building materials and components. And this has to be included. So every new production of concrete has to be considered. Then you have the planning and construction phase, the completion. It's more or less the same as in the life cycle cost. The operation and use phase. In this phase, in terms of environmental impact, of course, the energy consumption is the main part which causes environmental impact. Then you have demolition and disposal in the standard consideration, and then you have recycling and recovery. For our analysis, we do not consider everything. It's because it's very complicated. It will be considered things according to the standards ISO 14040 and ISO 14044, which gives the basis to calculate the GWP, the global warming potential, with the unit kilogram per CO2 equivalent, and the PNNRT, which is the renewable energy consumption during the whole phase of the life cycle, which the unit is megajoule. These parameters measure the life cycle-oriented environmental sustainability. Let's go to consider this for a modern building and for an historic building, which we have done in our research. So this is a more or less ideal example we have chosen. It's a real, these are two real buildings located in Krems, in Fischergasse 5 and Fischergasse 9. And we have the luck that you have an ancient heritage building, which is called the Wallseerhof on the left-hand side, which was refurbished totally in 2009 up to 2010. And this then became a dwelling building with 6 dwellings inside. And there was also constructed a new twin, so to speak, a new construction, also with 6 dwellings. If you consider the figures, you can see in terms of heated area, the two buildings are more or less equal, and there is no big difference. And this is a very good chance to compare how does an old building and how does a new building behave, considered over the life cycle. This was really a big task before, because we had to organize and collect all data necessary for doing this calculation, which is really the most heavy burden you have to bear, of course, excuse me, to bear for the calculation. This is, here you can see a little modified the life cycle concept for the historic building. So for the historic building, there is no new construction, there is just a general refurbishment, and there is, of course, the past of the monument. And then in this calculation for the environmental life cycle, we have considered a lifespan of 50 years, starting with the year 2011 and up to 2060. And then in the future, and this is mandatory, of course, there will be likely a refurbishment calculated in the year 2061, and then we'll start the next cycle. Due to the definition of Brundtland, so the next generation will have then, or should have then, the chance to have the same possibilities as we have had in 2010 to make a new life cycle for this historic building and to prolongate the life of this building. This is the concept for the historic building. And then we have the new building. It started in the same year with the construction. Then we have the life cycle. And for this building, we do not make any predictions for the future, 2061. In a calculatory sense, it will be demolished and disposed, but it could also be, of course, refurbished, and a new life cycle could start. This will depends upon the decision in the year 2060 of the next generation. So now I will show you the results. Very interesting. You can see on the left-hand side the total amount of global warming potential in in the unit of kilogram CO2 equivalent. And you can see for the whole building over the whole 50 years, or let's say 51 years, because it is also included in 2010, the refurbishment. And on the right-hand side, you have the same amount for the new building. You can see that the new building has at least 20 to 25% more consumption of CO2 equivalent than the old building. Why is this so? Consider the two parts of the columns. On the left-hand side, the building construction part, that's the second one from the bottom. This building constructions is less than 200,000 kilograms CO2, so about 180,000 kilograms, 180 tons, you can say, is used for refurbishing, for putting in new bricks, putting in new concrete. And on the right-hand side, the whole construction of the building has to be done, which means you have about 450 tons of CO2. So this is the main part of the total CO2 consumption over a life cycle of 50 years or 51 years of a building. If you compare the heating, we have on the left-hand side the old building. Of course, there is no outside insulation. So the consumption of CO2 of the heating, they have, by the way, they have the same heating systems in the old and the new building, absolutely the same. You have about 180 tons heating CO2 produced over 50 years. And on the right-hand side, the new building, which is very energy efficient, has just 80 tons of heating. But you can say this does not bring much to the total consumption of CO2. So the basic message is refurbishment and new construction gives the main part of CO2. And we have really to consider for the future, for the Green Deal, that we don't build too much new buildings. And it's always the better choice to make a refurbishment of an existing building, because Europe is more or less built. So we have buildings, and it is our duty to choose always the refurbishment and not the demolition and new building. My last transparency shows the life cycle costs. Also here, this was a slight different calculation. We considered just 40 years, which is a little bit an advantage for the historic building. So, but if you consider the results very coarsely, you can say the historic building is slightly better, but not worse than the new building in terms of life cycle costs. It is also, these are the costs in euros, 2.5 million euros. I have to add, these are costs without value-added tax. So roughly you can add 20% for the value-added tax, more or less. Then you have then the results, including value-added tax. And you can see the top part of the column is the heating. And here you have the difference. The old building has, of course, not only the CO2 consumption, but also the euros in paying the heating on the left-hand side and paying the heating on the right-hand side. I would add to this that this is, of course, a prediction. So we don't know in how far the heating will be, let's say, in the year 2030, 2040, 2050, if it comes from total renewable sources, then it makes a smaller difference, because heating in the terms of CO2 does mean that the old building has a bigger advantage than compared to the new building. And in costs, it will not change very much, because this is a question of the market. So these are my results of the presentation, and I hope I have given you a deep insight. What does it mean to consider economic and environmental life cycle consideration of a building? Thank you very much, ladies and gentlemen. I'm now open for questions.
Thank you very much, Dr. Floegl. Does somebody have questions to the topic or to the lecture?
I may. I also would like to thank you, Helmut, for the interesting lecture. I knew about this project before, but what I would like to remark on this is one thing that as you had the buildings standing.
Excuse me, I must interrupt. I do not hear. My sound is very low, so I can't hear it. Ich höre fast nichts. So 1 second, it will be fixed.
It will be fixed.
Lauter. Peter, kannst du was sagen?
Ja, Test 1, 2.
Okay, now it is okay. I can hear you clearly.
I just wanted to remark that it came to my mind when you had the picture of those two buildings standing next to each other. It was interesting that not only the difference in the CO2 equivalent balance is different, but the quality of architecture is something which is a certain aspect which we should consider as well, because the new building for me is not so nice and not so it seems not to have the value as the old building. And considering this fact, it's an argument for really considering reconstructions as the better way. So
yes, I totally agree. I totally agree. This was not considered, and this, of course, it was on purpose not considered, because I want present, let's say, the naked figures, the naked numbers of the construction. Of course, and this is for me the third column, the social cultural sustainability, the urban feeling, the feeling that this is part of your identity, the historic building. It's much better represented than by the new building. And this, I totally agree. But if you consider we are in an economic world where the numbers of the euros count, and if something doesn't calculate, if something there is no revenue, no benefit for a developer, he or she will not develop the building. And my message is that, of course, this advantage of the old building, this is the base, but we can argue also on an economic and especially on an economic reason for protecting our world. It's better to refurbish the old buildings than to build new ones. That is the main message. And of course, also to say it does not cost more if you do that and not tear down the old building and build a new one.
Mm-hmm. Yes. Maybe I have a question regarding the operation costs and the maintenance of the building. In the new building, the costs are, I think, higher as I read the graphics. Is it because of the new technology which is introduced, which is more costly to maintain?
Thank you for the question. That was because that was a little, you have to take a lot of normative assumptions for the calculation of these costs. But we have the luck in these two buildings that we have real costs from the year 2011 up to 2018. And these costs, this was the real costs of both buildings, of each of the buildings. And these costs have been, of course, extrapolated for the future up to 2050. So this was the normative assumption. And it turned out that the new building had more to repair, more costs in maintenance than the old building, which was for me also a little bit astonishing, because normally one thinks that the old building needs more maintenance than the new buildings. But it turned out, especially for these two objects, that this was not the case. And it's also the heating costs. Heating costs were extrapolated from real costs from 2011 to 2018 we had, and this was extrapolated up to 2050. That was the base of the calculation.